Hi, and welcome back to another episode of this Study With Me series, learning some more of the concepts and math behind quantum mechanics. This episode is going to be a little bit of a step back from the previous two, and we're going to look in more detail to truly understand what it means to observe and measure a quantum state. If you haven't seen the previous two episodes, don't worry so much. None of that math is really going to come into this video, but I hope that all of it will come together in the next video after this. So let's start off. We're on Brilliant and we're in the Quantum Objects course. We're looking at what it even means to be dealing with quantum particles. So atoms are certainly small enough to behave as quantum objects, but they're very, large on this relative scale, and they contain many complex parts. So what we're going to use in some experiments here is the neutron. This is a particle that's in the atom, makes up the nucleus, and the neutron doesn't have a charge, so it is neutral. A lot of work went into understanding neutrons around the time of the Manhattan Project, when they were involved as an important part in making nuclear power plants and atomic bombs. They relate to moderating the nuclear chain reactions that go on in these processes. So that was, where a lot of the interest in neutrons came from. But what we're going to be using neutrons here for is something I have mentioned before, which is the Stern-Gerlach Experiment. And that is something where you fire neutrons through magnets and you learn about fundamental quantum properties such as spin. So in this picture you can see here we've got a hot nuclear oven, and it is spitting out a single neutron. One of the first questions here to establish some understanding is, what kind of path do we expect this ballistic neutron to take? Now, I actually got this wrong. I wasn't paying so much attention. The answer is that the neutron will continue to travel in a straight line. It's not going to be slowed down by drag, because drag depends on friction with the air you're moving through, and it depends on surface area. So the surface area of a single neutron is so small, it's going to be negligible in this case, and is definitely not going to be pulled down by gravity either, because on the scale, gravity is going to be way too small as well. So we can ignore those factors and know that if you fire a single neutron, it should just continue to travel in a straight line, provided nothing else happens to it. So here we're introducing a first complication. We are firing our single neutron, and we've arranged two magnets of opposite polarity. That means one is like a north pole and one is a south pole, to create a magnetic field perpendicular to the path of the neutron. So it's going to travel through the magnetic field. Given our understanding of classical physics, how might we expect our neutron to be affected by the magnetic field if we treat it as an uncharged mass? So the answer here is that we would still expect the neutron to travel in a straight line, even through this magnetic field, because we're treating the neutron as we understand it as having no charge, and something would only be affected or deflected in a magnetic field if it had a charge. So yeah, we'd expect the neutron to behave like any other uncharged mass in a magnetic field and be unperturbed. However, this isn't what we observe. Our neutron's path is deflected, much like we would expect from a charged particle like an electron or a proton. But it is to a much smaller degree, its deflection. Because this neutron is, unexpectedly deflected in the magnetic field, it means something else is going on. The neutron is uncharged, so this deflection implies that the neutron has what we call a magnetic moment, essentially that it acts like a tiny bar magnet. This is where the definition of spin comes in. So uncharged objects sometimes have magnetic moments if they are spinning. So the experimenters here referred to this magnetic moment of the neutron as a spin magnetic moment. It has a magnitude and direction corresponding to the axis of the spin's rotation, and it behaves like a tiny bar magnet in a magnetic field. All right, so this tiny bar magnet here is how we're essentially modeling our spinning neutron. It's not necessarily physically spinning, it's just the fact that it's deflected by a magnetic field, and this is one way we might be able to explain that behavior. This page is talking about how our neutron, when going through the magnetic field, the amount of deflection would depend on, I guess, how the neutron is orientated. So if it's sort of tilted upwards or downwards, that would change the direction in which it is deflected by the magnetic field. It's also talking about how the force that the neutron will experience, that's the force deflecting it, will depend on the angle that it's spinning, a cos theta, where theta is the angle between the magnetic field and the spin axis of our neutron. Okay, so different orientations should result in a different amount of deflection because you're going to feel a different force pushing you up or down. The idea here is that if we place a particle detector after the magnet, we can measure how much the neutrons have been deflected and then infer which direction its spin was directed. Okay, so that's what this picture here is showing us. All right, so we've got another question. We've already fired one neutron through. We go to fire a second one. What do we expect to be its deflection? The correct answer was that the deflection should be random. It should be deflected by some random amount, I guess, based on its initial spin axis and how it was orientated in the magnetic field. All right, so now we are generating a constant stream of neutrons emerging from our little oven and heading through the magnetic field and onto the detector. So again, a very similar question. What would we expect the distribution of this constant stream of neutrons to look like on the detector screen? The answer is that we would expect to see a continuous distribution centered around 0. So these would all sort of hit randomly along here based on how they were orientated. Okay, so here's where the kind of strange thing comes in. Whilst that is what we would have expected, our classical expectations for how the neutrons would be deflected, neutron spin does not behave like a classical property, and we get something that's a bit of a surprise. So instead of seeing this continuous spread of neutrons, we get two distinct bands, one at the top of the detector and one at the bottom. So according to our analyzer, neutrons are only found in two possible states out of the infinite number of random orientations which they could have had. Spin must be a quantum property because it is quantized. That means it comes, I guess, in discrete packets. It's only allowed to have certain values. Please leave your classical expectations at the door. So this is really an introduction into why aspects of quantum physics become really surprising. All right, we're heading over into the next section. We were in classical expectations, now we're off to quantum surprises. Before we go any further here, I'm going to recap the Stern-Gerlach analyzer, which is actually just what we've been talking about, but let's just recap some of the notation that's going to be used. So this is the analyzer. It just consists of a neutron coming in, that magnetic field that we saw, and this analyzer is able to distinguish the output into two possible things, spin up or spin down. So those are essentially those two bands we were seeing on our detector screen. The brackets around our spin up and spin down arrows are called kets, and they're a way of referring to the state of the particles in each channel, so either the up channel or the down channel. Similar brackets are around our input here, which is around our wave function, just saying that that is, I guess, our mystery state before we figure out whether it's spin up or in the spin down state. This question here is saying, okay, you've been running the experiment for a while, you've got your Stern-Gerlach analyzer, you've got your two output channels. How do you expect the neutron states to be distributed between the spin up and the spin down state? And the correct answer is that you would expect a roughly even 50-50 distribution. Half of them are up, half of them are down. Then, brilliant, the website starts to talk about how this probabilistic behaviour is at the heart of quantum mechanics. We'll touch more on that later, but essentially they're using now as a chance to talk about how, we've got these 50-50 distributions with seemingly no way to figure out whether a certain particle will go spin up or spin down, but averaging over all the time, you get a 50-50 probability. It seems a very random process. Okay, so we're going to extend the experiment a bit here, and the first part of it is just our ordinary experiment we've been talking about. We're going to add a second Stern-Gerlach analyzer such that the output, which is in the spin-up state, will become the input into our second analyzer, and then again it will split it into being either spin-up or spin-down. We were asked what we expect the distribution to look like as it emerges from these two output states here. Okay, and the correct answer is that all the neutrons emerging from this analyzer will be in the spin-up channel. So even though there are two possible options, all of the neutrons will remain spin up because this second Stern-Gerlach analyzer is essentially repeating the filtering process that's already gone on in the first one. Everything that emerged from here was spin up, so everything passing into here should be measured spin up again. If you measure it twice in a row, you will expect to get the same thing. This result doesn't just hold for two analyzers in a row. You would expect to see that if you place an infinite number of these analyzers one after each other, such that you're always, using this spin up result as the input for the next analyzer, at the very end of this infinite chain, you will still be measuring all of the neutrons to be spin up. Just to check how things were working, when they did these original experiments, they thought, okay, well, what if we flip the second analyzer upside down? That means that the magnet would be essentially flipped. The north and south poles of the magnet would be on opposite sides. And then we, used the spin up as the input state for the second analyzer, which is flipped. What would you expect the result from that to be? The correct answer is that all the neutrons would emerge this time from the spin down channel, so they'd be measured down here. It does kind of make sense because literally you have just turned this analyzer upside down, so even though you're measuring them now as spin down, you're really still doing what you're doing before. You're measuring them as spin up. You've just flipped which way the up and down channels are appearing to you. All right, let's move on to the next chapter, which is Observables. This chapter is starting off by talking about a spinning top. So this is just a classical spinning top, like a toy. And they're saying that we could observe the X, Y, and Z components of its spin axis, so that's just what angle it's on, I guess, in three-dimensional space, to find its spin vector. You could also have angular velocity and kinetic energy as physical observables associated with this spin. These are things we could figure out about the classical spinning top toy. The easiest way to measure the direction of the spin vector would be to rotate your perspective. You could take a photo from, the top, the side, and the front and get these different images, and you'd be able to figure out everything you needed to know about this spinning top. This part down the bottom says that we've had some success understanding neutrons as microscopic spinning tops, even though the spin vector can only point up or down, and that's a little bit odd. Let's see if we can measure the other neutron spin components with an SG analyzer by rotating our perspective. That means finding out more information than just on the one axis we've been looking at. So yeah, this is how we've currently been looking at the experiment. This is the Z direction, the straight up and down. That's the way our magnet has been aligned, and that's the only axis on which we have any information. So to gain more information about the spin vector of these neutrons, we could rotate our analyzer by 90 degrees. So now the magnet is flipped so that it's aligned on the x-axis, so from left to right. And this should help us to gain actually some more information. So from our understanding, what would we expect to observe from the second Stern-Gerlach analyzer when it's aligned along the x-axis and we're feeding in our experiment we've already done, where we're feeding in the spin up input into it? The answer of what you would expect to see is that the neutrons are not deflected at all. The reason why I picked this answer, and it's expressed down here as well, is that the z and the x-axes are orthogonal to each other, so at 90 degrees, and any vector that had been aligned along one of the axes has no component along the other orthogonal axes. That's a feature of linear algebra, and a feature of two things that are at 90 degrees to each other. There is no overlap. So we know that the filtered z spin directions, so that's essentially our input here, they've already been filtered to be completely spin up. They should not have any component in the x direction, so we'd expect them to not be deflected at all in an x-aligned analyzer. Alright, that's what we'd expect classically to happen. However, this is another surprise. This is not what we observe. We again see a binary result. So half of the neutrons are deflected as though their spin were aligned along the positive x-axis, and half as though they were aligned along the negative x-axis. So we still have half the neutrons coming out of each of these two channels. This is really strange because what it says is that a particle that had seemed to be aligned along the z-axis now seems to also be aligned along the x-axis. And a normal vector cannot be aligned along two axes that are at 90 degrees to each other at the same time. So this is really quite strange. You could repeat this measurement with other rotations of the analyzer and you continue to always see this binary result. The way that we explain this is that, spin is a quantum property. It can only be observed in a given set of quantized values. In this case, 0 is not one of those values, even though that would be the classically expected solution. But it does say here that there's a glimmer of classical physics remaining. If you repeat this experiment many times, you find that the number of neutrons, which had initially been measured to be spin up, and are now measured to be either spin left or spin right, they're measured an equal number to be spin left and spin right. So the average deflection through that second analyzer is 0. If you take the average of all of these spin left and spin right, you end up with being in the middle. Even though no neutrons actually got to the middle, that's still where the average is. And that matches with the classical expectation. So here's a really important idea, and it's in a box here. At the limit of many quantum measurements, the average will always approach the classical result, even if individual experiments appear to violate the classical law. This is called the classical limit. Alright, so this is quite important and goes on to explain how we get the classical world around us that makes sense from quantum physics, which appears to defy what we know. You can see this in another example here, which is a little bit more tricky, but still makes sense. So if you were to rotate the second analyzer by some arbitrary amount theta, which isn't 90 degrees, so here it's just been rotated a bit, classically you would expect the amount of deflection of the neutrons to depend on that angle. It would be cos theta. And in the quantum experiment, even though we still get this binary, they're either all the way at the top of the detector or all the way at the bottom, the amount by which they go to the top or the bottom means that if you take the average of all these positions here, you would still end up with this line of neutrons here at cos theta. You would still end up with the average, even though all you got was this binary distribution where nothing seemed to be in the right place. They actually average out to be what you would classically see. I guess this explains why a large part of quantum behavior seems so counterintuitive. Macroscopic objects, so something like a baseball, consist of a very large number of microscopic quantum particles, and we only observe their averages. We only observe the average behavior of the quantum particles unless we're doing these kinds of experiments and looking very closely actually at the quantum behavior itself. Alright, so let's keep going. It was a bit weird that our neutrons were aligned along two different axes that were orthogonal, but let's add in a third analyzer to the experiment, aligned just like the first one in the Z direction. Based on our results so far, what channel would you expect the neutrons to emerge from in the third analyzer? Okay, so the answer I chose is what I would classically expect, that all neutrons would emerge from the spin-up channel. The reason that I chose this answer was because, you know, when you didn't have this sideways one and you would have just put this one after this one, if you've measured it spin up in the first place, you should always measure it spin up again afterwards. That was an answer I was very confident on, and I was happy that it told me that I was correct. So this kind of blew my mind actually, but when you go to the next page, you find out that this is not what we observe. The neutrons leaving the third analyzer are again split with a 50-50 probability in the spin up and spin down states. Even though we diverted all the original spin down neutrons away from the experiment in the first analyzer. So yeah, that really sort of surprised me to actually have my classical expectations proved wrong in this experiment right here. So let's stay with it and try to understand why this happens. Essentially, how can we explain this contradictory result? The answer was that measuring spin along the x-axis, which is what we did in the middle, destroyed all previous knowledge of the neutron spin state. What this result demonstrates is another key feature of quantum behavior, again in another important box, and that's that quantum measurements are not as gentle as classical measurements. Sometimes measuring a quantum state can change the state for all future measurements. So essentially our unknown state, which emerged from our oven, was never really aligned along the positive or negative Z axes, but by trying to measure the Z component of the spin, we changed the state to being one of the two possibilities, spin up or spin down. Measuring another component caused the same result. The X analyzer reset our prepared spin up state into being one of two completely different possibilities, spin left and spin right. You might ask, can we be more clever in designing the experiment such that we don't disturb the system? But no, there is a fundamental incompatibility in trying to measure the spin component of a quantum object along two different directions. So we say that the X and Z spin components are incompatible observables. We can never know them both simultaneously. So revisiting our classical model of that spinning top toy, we see that not being able to measure both the spin Z and spin X components is completely different from the classical case where we could measure all the components of the spin vector easily at the same time. We could just take these three different pictures from three different angles. We need to determine all three of these components to determine which direction the spin vector is pointing, and for quantum objects, the different spin components are incompatible. We can never know which way the neutrons are pointing. When we say the spin is up, we really mean only that the spin component along one axis is up. This property isn't permanent, since measuring the spin along any other axes will essentially reset the spin. Okay, let's move on to the last section of this part here, which is measurement and memory. So what we encountered in that last section was the measurement problem in quantum mechanics. We could not devise an experiment capable of measuring the neutron spin components without destroying previously collected information along the way. It appears that the experimental apparatus we were using must disturb the neutron spins while observing them, making it impossible to precisely determine the direction of the spin vector. This interesting consequence of quantum mechanics is not limited to spin, as we'll see in later chapters. Well, spoiler, this is what I've sort of been talking about recently on my channel to do with the double-slit experiment, and how in that experiment we were using a detector to measure where a particle went, so its path through two slits, and how that act of observing collapsed the wave function. So this does relate to the measurement problem as well, but I'm not talking about finding the path of a particle here. Instead, we're talking about trying to measure its spin and how this also seems to affect fundamentally what's going on in the experiment, the act of measuring. I will say as a further disclaimer, which I did say in a previous video of mine, there's no reason to think that a conscious observer is needed as part of this process, but rather that information about the particle becomes available to an external environment. You don't need a human eye to be watching that data come in. It's just the fact that that data exists does impact the experiment. So let's examine this idea a little bit further. If we combine the spin left and spin right beams of neutrons, which emerge from our second analyzer, the way that we combine these beams shouldn't be important. We're using magnets deflecting the beams back into alignment, and we have to assume that these magnets here are not affecting the spin of the particles in any way. So we're regathering both our sets of neutrons back here, putting them through another Z analyzer, and what would we expect to get out the end here? When I answered this question, I said I would expect, based on what I know here, that the neutrons would be split evenly between both channels. The reason I answered this was because, when we weren't recombining the data, that's what we were seeing. We were seeing that this information of the initial measurement was lost. A new measurement is made, which essentially reset the data, and then this was reset to being, 50-50 up and down. That was the correct solution on Brilliant for what you would expect. But what really got me was that's actually not what we observe. So the result that we actually observe is kind of absurd and contradicts our expectations, but all of the neutrons emerging from the third analyzer here are in the spin up position, and this really blew my mind. I was like, what? I thought I was understanding this. But let's just have a little bit more of a look here to understand. So what has happened is that the X component was never actually observed, so the state wasn't reset. That means here, when we put in this X analyzer, because the data was arranged or set up such that it could not be observed, was rejumbled back into the third analyzer, the effect of resetting the quantum state did not happen. So let's see what they say in their words. Although the neutrons have gone through an X-component analyzer, which we've noted completely destroys information about the Z component of the spin, the X component of the neutron channels was never actually observed. Recombining the deflected beams, so measurement could not tell them apart, seems to behave as though the measurement never occurred. The neutrons still remember that they were measured to have spin up along the Z axis. So they go back to behaving as if this middle analyzer wasn't there at all, and it was what we saw before. If you input this spin up neutron into another analyzer that's measuring whether it's spin up or down, it will always, at an infinity of analyzers, continue to be measured spin up. It was only when we started to measure a different axes that we were resetting these spin values. But if we attempt to reset them and don't actually have the data in such a way that it's measurable, this resetting process does not occur. I'm sorry if you can hear meowing in the audio. My neighbour's cat is at the door trying to get me to feed it, which I'll probably do after I finish recording this. So what Brilliant says here is that the measurement problem is essentially more sinister than a disturbance caused by our magnetic fields. So what we might have thought was a shortcoming of the experimental setup turns out to be a reflection of something much deeper. It's the act of measurement itself that is changing the state of our neutrons. From the point of view of the neutrons, they were never observed, and no incompatible measurements have been performed that would reset their states. The role of observers in quantum mechanics is completely unique and has no classical equivalent. This fundamental quantum mechanical property is the most important we've learned so far. So here's our third important idea in a box. I'll read it out. Observers can change the state of quantum objects. Quantum states are reset by observation itself. Though the point in the experiment when this occurs is still the subject of active debate. I'm not quite sure what that last point means about the debate over which point in the experiment this occurs. Maybe they'll get more in depth into that, but I can't say for sure I understand what exactly the debate is there. If we try to understand what's going on here by analysing, I guess, the path of a neutron between two analyzers, an X and a Z aligned one, we can note the probability of the neutron emerging from each state. So this is using classical probability, the way we would normally do things like with a probability tree. So if we had a 50% chance of coming out of the spin left state, and then a 50-50 chance here, so this is actually a 25% chance of the original neutron ending up here. 25% chance of ending up here, 25-25. So you've got our four different options and a 25% chance of ending up in each of these places. But when we put each of these two results up here together, what we end up with is a big contradiction. We end up with two paths that were 25% each up here, adding essentially to 100, because this is where we see all of our neutrons ending up. And same here, we get 25% plus 25% equals 0 because none of our final neutrons ended up in this state. So we have classical probabilities not adding up to give us what we actually saw in this experiment. What can we conclude from these results? The answer is that quantum measurements can't be treated as independent events. So the way this would work in classical probability is that, you know, this 50-50 chance here is completely independent of anything else on the tree, of this 50-50 chance here, and of things that have happened previous to it. In classical probability, every time you branch out, this is, I guess, an independent event, but our quantum measurements can't be treated like that. I hope the way that I've described this idea here makes sense, because I didn't use a lot of math and I really wanted to give a good primer to some of the quantum ideas that are going to be involved, because in the next video I want to jump back into the mathematical foundations and use the math actually that we developed in the previous two videos to this one. So that's this stuff, you know, the linear algebra and Dirac notation, to actually describe this experiment very mathematically and understand the approach, and it's called the Feynman path integral formulation, or summing over all histories. So there's a lot more cool stuff we can do, and I hope that the next video I make is going to bring together all the videos so far. So all this knowledge, if you've been following along with me, bringing it all together to have quite a good way of mathematically describing and interpreting these experiments, and I kind of look forward to doing that, and I hope to see you again in the next video. If you don't want to wait for me to make that next video, I encourage you to jump on brilliant.org yourself and work through at your own pace. You can try some of those questions that pop up on the side, and there's a lot more material on this website than I could ever cover. So if you want to learn more, I think you should go onto Brilliant yourself and have a look. Brilliant are a supporter of my channel, so you can go to brilliant.org/Tibees and sign up for free. And the first 200 people that follow that link can get 20% off an annual premium subscription. So thank you to Brilliant for helping me to continue make videos. I'll see you guys in the next episode, and in the meantime I'll be reading your comments and hoping that you guys have learnt some stuff along this journey as well, and it'd be interesting to see what further questions you have and what you'd like to learn about more. See you then.